NENOMATICA, where mathematics meets YouTube excellence. Welcome to today's math lesson. We're going to explore an interesting theorem about cubic equations with rational roots expressed as fractions. Let's look at the theorem we're going to prove today. If the cubic equation ax cubed plus bx squared plus cx plus d equals 0 has rational roots in the form of p over q, where p and q are integers, then the number p divides the constant term d, and the number q divides the coefficient a. Now, let's prove this theorem step by step. We'll start by assuming that x1, x2, and x3 are the three real roots of the cubic equation ax cubed plus bx squared plus cx plus d equals 0. From Vieta's formulas, we know that for a cubic equation, the product of all roots is equal to negative d over a. Now, if the roots are rational, we can express them in the form of fractions. Let's assume x1 equals p over q, x2 equals p prime over q prime, and x3 equals p double prime over q double prime, where all p's and q's are integers. Substituting these into our product formula, we get the product of p over q times p prime over q prime times p double prime over q double prime equals negative d over a. Let's simplify this equation. We can rewrite it as the product of p times p prime times p double prime divided by the product of q times q prime times q double prime equals negative d over a. Cross-multiplying, we get the product of p times p prime times p double prime times it equals negative d times the product of q times q prime times q double prime. Now, let's rearrange this to get our desired conclusion. First, we'll move the negative sign to the left. Negative p times p prime times p double prime times it equals d times q prime times q double prime. From this equation, we can see that d is a factor of the product of p times p prime times p double prime times a. Since all p's are integers and they divide the right side, which contains d, we can conclude that p divides d. Similarly, since it is a factor of the product of d times q prime times q double prime, and all q's are integers, we can conclude that q divides a. Let's summarize what we've proven. We started with a cubic equation with rational roots expressed as fractions. Using Vieta's formula, we established that the product of the roots equals negative d over a. By substituting the rational roots and manipulating the equation, we proved that p divides d and q divides a. This is a powerful theorem that gives us information about the relationships between the coefficients and the roots of a cubic equation. Thank you for watching this mathematical proof. This theorem is particularly useful when finding rational roots of cubic equations and can help us understand the structure of polynomial equations more broadly. Remember to practice applying this theorem with different examples to solidify your understanding. We'll be working with the equation 16x cubed minus 60x squared plus 56x minus 15 equals 0. We'll solve this step by step following a specific algorithm. First, we'll use the rational root theorem to list all possible rational roots of our equation. According to the theorem, if p over q is a rational root written in lowest terms, then p is a factor of the constant term, and q is a factor of the leading coefficient. For our equation, the constant term is negative 15, and the leading coefficient is 16. So p could be plus or minus 1, 3, 5, or 15, the factors of 15. And q could be plus or minus 1, 2, 4, 8, or 16, the factors of 16. This gives us many possible rational roots to check. Let's take a pause to think about which one we might try first. It's often best to start with simple fractions like 1/2, since they're easier to compute with. Step 2, let's test if x equals 1/2 is a root. We'll substitute x equals 1/2 into our original equation and see if it equals 0. 16 times 1/2 cubed minus 60 times 1/2 squared plus 56 times 1/2 minus 15. 1/2 cubed is 1/8 and 1/2 squared is 1/4. So we get 16 times 1/8, which is 2, minus 60 times 1/4, which is negative 15, plus 56 times 1/2, which is 28, minus 15. This simplifies to 2 minus 15 plus 28 minus 15, which equals 0. So x equals 1/2 is confirmed as a root of our equation. Step 3. Now that we found x equals 1/2 is a root, we can factor out x minus 1/2 from our cubic equation. For a cubic equation, if lambda is a root, then we can factor it as x minus lambda times a quadratic expression. Using polynomial division, When we divide 16x cubed minus 60x squared plus 56x minus 15 by x minus 1/2, we get the quadratic factor 16x squared minus 52x plus 30. So our equation becomes x minus 1/2 times 16x squared minus 52x plus 30 equals 0. Step 4. Now we need to solve the quadratic equation 16x squared minus 52x plus 30 equals 0. Can you solve this quadratic by factoring or using the quadratic formula? Let's use the quadratic formula. For a quadratic equation, ax squared plus bx plus c equals 0. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. In our case, a equals 16, b equals negative 52, and c equals 30. Let's first calculate the discriminant. That's negative 52 squared minus 4 times 16 times 30. That's 2,704 minus 1,920, which equals 784. The square root of 784 is 28. Now we can find the two values of x. It's 52 plus or minus 28, all divided by 32. That gives us x equals 80 divided by 32, which simplifies to 5/2. And the other value is x equals 24 divided by 32, which simplifies to 3/4. Now that we've found all the roots of our cubic equation, let's summarize our answer. The roots of the equation 16x cubed minus 60x squared plus 56x minus 15 equals 0 are x equals 1/2, x equals 5/2, and x equals 3/4. Let's summarize what we've learned. We used the rational root theorem to list possible rational roots in the form p over q. We then tested the simple fraction 1/2 and found it was a root. Next, we factored out x minus 1/2 and got a quadratic equation. By solving that quadratic, we found the additional roots 5/2 and 3/4. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.